Let me show you something important. So this is a set of a couple dozen pressure tests that we ran on Intel 12th gen CPUs. And the reason we ran these is because in our lab testing, we discovered an interesting trend where, as you can see here, 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 and basically in all of these tests, the entire right half, including the die area of the CPU IHS, is lacking pressure. And that shows up here on an actual CPU. The reason for all of this is because of this. This is the Intel ILM, or the independent loading mechanism, that is on motherboards to secure the CPU in the socket, but it provides uneven pressure across the surface of the IHS, and that is a problem. That's why today we're investigating this by swapping the Intel stock ILM with this aftermarket option, the Thermal Grizzly CPU Contact Frame. We're going to be testing these for pressure and for thermals to see how they perform and if the issue of bending Intel CPUs magically goes away. Before that, this video is sponsored by Linode. Linode is a Linux server hosting provider that GN has used for nearly a decade now for its own servers. Alongside dedicated website hosting, Linode makes it easy to cut out third-party VPN services to build your own VPN that you fully control, easily configured via the interface. Linode also has hundreds of guides for custom servers, including game server apps like Rust, Minecraft, CSGO, and guides to host your own video calling servers to eliminate third parties. Linode is a great way to take back control of software and your hosting, and Gamers Nexus viewers get a $100 credit for 60 days on new accounts at linode.com/gamersnexus, or click the link below. Now, this might not look like a $35 piece of metal, but it has tight machining tolerances that are meant to resolve the issues of the Intel ILM. We've deconstructed one here, so you can see that it has just 2 core pieces and then a couple of screws. So with the contact frame, it's supposed to be solving the CPU bending that the Intel stock ILM is accused of causing. Here's how that's happening. The Intel independent loading mechanism, or the ILM, is this thing. It's pretty simple. The mechanism uses an obvious lever and spring design to apply an intimidating amount of pressure to the CPU to hold it into place. But the lever isn't the only spring point. The footing towards the bottom of the socket also behaves in a spring-like fashion. It flexes and intentionally warps as pressure ramps to conform to the surface of the CPU and the socket itself, but in a way that doesn't permanently bend the socket. In theory, inside the socket, there are a few black pads to help take the bite out of the contact between the metal of the socket retention kit and the CPU IHS. All of this pressure, it's important. Intel has 1,700 pins in these sockets, and if those pins don't directly contact the right pads on the CPU with the right pressure, you can have instability or loss of functionality. This is actually something that Thermal Grizzly warns against with its own kit that we're reviewing today, because they warn that over-torquing it causes potentially bad contact with pins that could reduce memory frequency or clocking potential. And that's the most common loss. It's typically memory channels or poor memory stability. With poor contact at even just one pin, whether from pressure that's too low or from debris in the socket, we might lose an entire memory channel. We could also lose the frequency range or less obvious losses. But if you really look at the socket, it only has 3 real points of contact. It contacts here, here, and up here at these 2 flanges to a single bar coming off of the lever for the independent loading mechanism. And that's why there's this huge amount of play side to side in the socket. You can secure it all the way off to one side, the other side, right in the middle. It doesn't really seem to settle in one particular place. So all of that pressure is getting applied up here initially, which is causing flex in both the board and the socket. And if you look at the CPU when applying pressure, you can see it sink deeper into the socket as the pins depress and make contact with the pads. We've noticed that the lever is just slightly pushing down a little bit harder on the right side of the socket, and that's tested across multiple boards. The spring design applies unevenly high pressure to the RAM side of the CPU, which causes a slightly lower surface than on the I/O side. And by slightly, we're talking basically microns of difference here. This results in a few things. Mainly, it reduces overall thermal performance of the CPU. We'll look at that later in some charts. As a result of the uneven pressure right in the middle of the CPU, where the die is, and too little pressure towards the RAM from the actual CPU cooler to the IHS, the left side receives the highest pressure with this ILM design with the coolers we've tested, which means that the cooler cold plate itself will have uneven contact pressure across the IHS. This could cause small air gaps that get filled by thermal paste, and while that's the job of thermal paste, it's ideal that the air gaps are relegated to imperfections in the surface of the IHS and the cold plate and not a result of the mounting hardware itself. Additionally, this design can cause higher core-to-core thermal deltas when working with extreme cooling solutions. Some cores on the CPU will run cooler than others as a result of the mounting pressure or density of the thermal paste layer, becoming particularly noticeable in XOC environments. So, let's prove the problem with some testing from the lab. Our pressure testing uses a chemically reactive film that we then scan with a National Institute of Science and Technology traceable scanner that our viewers funded with their Patreon support at patreon.com/gamersnexus, where you can get bonus videos. We just published a new one, and via our GN store purchases at store.gamersnexus.net. Thank you to our Patreon supporters and purchasers for helping us out. For the first set of tests, we tested with the Intel Pentium G7400, the i9-12900KF, the i9-12900 non-F, the i7-12700, and the i9-12900KS. That gives us a total of 5 CPUs to test against, which allows us to have better sample size since the IHS itself matters here. We have a mountain of existing data for coolers on our AM4 CPU cooler test bench, so we have a strong understanding already of the cold plate designs and which would be the best used here. To get you all introduced, here's just one pressure scan from the test set. We'll overlay it on top of an Intel CPU just to help illustrate things. Overall, you're looking at relatively low pressure compared to some other tests we've done in the past, but the edge closest to the RAM doesn't even detect on our scan. The CPU only has good pressure over half of the die and half of the IHS. That's horribly inefficient and indicates an issue with the ILM. As we already know, the cooler and the mounting hardware are known good and provide a relatively even mount. We eliminated the cooler as a variable with additional test data. Here's the first set of results. The i7-12700 that we tested produced extraordinary results with the Thermal Grizzly frame. It's at nearly perfectly full coverage, sans a slight reduction in pressure in the center. The overall increased coverage and reduction in the off-canter mount is more beneficial thermally than that missing central coverage. The stock Intel ILM was lacking coverage centrally and toward the RAM, showing that the Thermal Grizzly Contact Frame does what it claims. It does work. This shows an Intel i9-12900KS. The left has the ILM from Intel, presenting lacking contact centrally and at the bottom half of the CPU. The Thermal Grizzly frame is on the right. This one produces smooth and even contact across the entire center of the CPU, most critically, and it also improves contact except at the topmost edge. But the loss here is far outweighed by the gains everywhere else. So far, this is an improvement. This one shows the i9-12900 non-K CPU. The Intel ILM shows the same lacking contact overall, though one of the two passes fared better than previous results. The Thermal Grizzly frame produces a demonstrably even pressure distribution, creating almost a perfect rectangular representation of the Alder Lake CPU underneath. This is a matter where IHS run-to-run variance is impacting the result, of course, and that's exactly why we spent 2 days running this many pressure tests on this many CPUs. But even with the sample size we have and all the retests we have, it's clear that the contact frame is doing a better job evenly distributing the load. The thermals are up next. So for this, we ran all of our testing on a Gigabyte Z690 master motherboard. You can see this in some of our installation footage we took. And we ran a minimum of 3 test passes with 2 to 3 complete remounts per socket type. So we'll do multiple test passes for the first mount, and then we add additional mounts after that. So through all that, we only had a variance on average of about 1 degree Celsius, and the CPU ran to steady state thermals before pulling the average over a few hundred rows of data per result. So we're averaging averages over hundreds of rows, which gives us very accurate data. The result showed an improvement in the Thermal Grizzly Contact Frame of about 7 degrees Celsius reduction, and that's a real improvement. That is far outside of variance. We didn't even need to lap the CPU to achieve a 7-degree reduction, so that's a big change for just a socket swap. The maximum core temperature pulled down by about 8 degrees Celsius, giving us more thermal headroom for overclocking when you look at the max single core temperature, and our clocks are limited ultimately by the hottest core when overclocking, so core-to-core deltas and maximum single core temperature matter. The core-to-core delta increased by about 1.4 degrees, but it's still a very wide gap at 20 degrees for the average delta core-to-core at any given interval in the test. And this is what lapping would help you improve more than anything else. And as a reminder, for these numbers, the average core temperature and the max core temperature, those are over ambient. So it's a delta T over ambient, where we're taking out the ambient temperature measured every second of the test from these presented results, except for the core-to-core delta, because that would be dumb. So bringing it back to that side-to-side wobble we saw a second ago, where it goes like this, we were curious when doing the testing, and so I asked Mike to try securing this with a bias of the ILM towards the VRM, towards the RAM, and then as centered as he could get it. And the result is this set of data. It's very simple. We didn't even bother scanning it. So for this one, the CPU is oriented like this, and the RAM is that direction towards you. So this has the i9-12900KS for all tests. We socketed it with the bias away from the RAM, and the result looks very similar to the result with the bias towards the RAM. Little bit of a shift here in some of the pressure profile, but especially if you look at these two, we did 2 passes of each. They are very similar. So slight change, but not much. Functionally the same. Centered, same thing. We have largely the same type of result. This is the best out of all the contacts we did for this set of tests, but still has lacking pressure compared to the contact frame that we tested with earlier. This Intel version of an ILM on the desktop CPUs, though, it's not the only way that it's done. In fact, Intel itself does it a few different ways, but so does AMD for Threadripper. So we'll grab 2 more boards to help show other approaches to designing an independent loading mechanism. First of all, on the Intel X99 and X299 class of board, which is this one here, you can see that the way they used to do it, since this is a dead platform now, was by doing actually 2 levers on opposing sides, clamping diagonally opposite each other. And this is one of the best sockets we had ever worked with, at least up until Threadripper. So these work by pressing in. Actually, you can only release one side specifically, and it's not that one. So you release over here first. The pressure is all applied down here by this much longer bar that sits within this footing grabbing it. So you release that pressure, then over here release the pressure, and again, much longer bar here. Then we have on the desktop class CPUs applied across a wider surface area and counter to the original bar. Comes up and it's released. Simple enough. Additionally, the contact patch is much wider. We have contacts here along the bottom of the IHS, and it's a much wider or larger surface, if only because the CPU itself is larger, but that helps to distribute some of the load more evenly than we see in modern desktop parts. And the problem with these desktop parts, these didn't used to be this big. They were typically around 1,100 pins. Now they're up to 1,700 pins, and they're going to 1,800, and that is why we're seeing some of the challenges we're seeing with that somewhat medium-sized ILM. Now, all of that is contrary to this one, the Threadripper ILM, where instead of all the stuff we just looked at, it makes complete contact around the entire edge of the IHS. This is easily the most secure CPU socket we've worked with in a long time. It's got the 3 contact points for the screws, but the metal itself applies pressure everywhere. And then you can even see this serious spring down here to assist with some of that tension. And then there's the clamps that you use for the actual install for dropping the CPU, which is footed right here into the socket. So those are other options for socket design that don't have quite the same problem as this one over here, but they're much more expensive. And that's what it comes down to. So for Intel, doing the cheaper ILM that they do now, well, it's cheaper. So it allows them to get into boards that are closer to the $70 price range. Thermal Grizzlies at $35, it's really not bad, especially if mass-produced by a company like Intel. It's the machining that costs money and the fact that Thermal Grizzly does low volume compared to a company that makes millions upon millions of sockets. So that's where part of the cost is. But the bigger issue with something like this, with the idea that Intel, why doesn't Intel just put the Thermal Grizzly contact frame or something similar on its desktop products? It's just a danger for the user, because most average users, you don't want to trust them to have the pins that exposed and to have to tighten the screws to the spec that this requires. So that's the issue. It's not hard for people in our audience especially, but for the average mainstream user, it could be a challenge. And to assist me in demonstrating that challenge, I am going to recruit Mike from our lab team to show the installation process of the contact frame and to talk about some of his concerns with it mechanically as an end user and just in general, because it wasn't all easy. It's not something we recommend for everybody, even though there is an improvement.
Okay, let's talk about the installation. Now, the installation is not complex, in fact, far from it. It only requires 4 screws, but there is a lot of potential for damage or doing it wrong. One of the risks of doing damage is to the socket. Now, DeBauer recommends leaving the CPU in the socket during installation, and I certainly found that to be advisable while doing the installation. Having those pins exposed while you're moving screws over or moving the frame over the socket itself is definitely risky. Because if you drop it and you bend those pins, it's very hard to get them correct again. The other point of contention or the other potential risk when installing this is too much torque or too little torque. Now, the manual calls for 0.03 to 0.06 Newton meters. Now, that's a very small amount of force, and it's hard to replicate without tools. Now, DeBauer and Thermal Grizzly have advised a certain technique that we're about to go over here. So all of the Intel 1700 boards are going to have a plate on the back of the motherboard that's held in place by the 4 screws you just removed. So as you can see, I still have the Liquid Freezer 2 mounting bracket hardware still installed. And what that's doing for me is it's holding the back plate in place so that it doesn't fall. And that way I don't have to hold it and try to install the frame while holding the plate up from the bottom. I think that's the only good way to do it, if I'm being honest. I've got that all set up, so let's go ahead and put our contact frame down. Now, the best method that I found was a combination of what DeBauer advised and a little bit of a tweak on my part. What we're going to do is we're going to back the screws out counterclockwise, so we're like we were taking them out until we feel the threads fall into place. Now, if you're mechanically inclined, you've probably heard of this or done this before, and that just prevents cross-threading. And of course, you definitely don't want to cross-thread these or muddy up the threads because it's going to make torquing it properly very difficult. So I'm going to go ahead, I'm going to back this screw out, and I hear and feel it fall into place, and I'm going to give it 90 degrees. And I'm going to go diagonally across to the screw caddy corner to the one I just did, and I'm going to do the same thing. Hear it fall into place, give it 90 degrees. One of the reasons I'm clocking the screws is so that I know that they're all threaded in equally right now. If I were to just start tightening down until I felt some amount of resistance, the frame is going to walk up and down. I found that to be, it gave me inconsistent results when I was mounting the frame. So now I know that each screw has about 90 degrees on it, and I'm going to continue to just add a set amount of rotation to each screw. So I'm going to go ahead and move to 45 degrees of rotation, and I'm going to go around to all 4 screws until I feel some very light resistance. And I now feel that resistance on all 4 corners. Okay, so now we're going to do the prescribed Thermal Grizzly method. So what they advise is that you turn each screw 90 degrees. Earlier, we marked our screws, and this is also what DeBauer and Thermal Grizzly recommend. So I've got these witness marks on the frame, and now I've got witness marks on the screws. So I'm going to go around all 4 corners, and I'm going to give it a 90-degree turn. And that's it. I had the most consistent results with getting it to post and boot using this method. It's a little step further as far as attention to detail than what DeBauer and Thermal Grizzly recommended. But if you have the patience, and I would recommend that you find some patience to do it this way, you'll probably have good results. Obviously, there's a lot of room for error with this. If you over-tighten the screws, you're going to potentially damage the socket, and you're going to lose contact. If you don't tighten them tight enough, you're going to also lose contact, and your system won't post. Overall, The fit and finish of the product is pretty fantastic. I think I was personally impressed with the quality, certainly the machining quality and the tolerances that they were able to achieve. It's a piece of 70-75 aluminum. It's anodized. DeBauer talks a bit about how difficult it was to anodize this properly so that it's not conductive. The logo and name of the product, as well as the witness marks for timing your screws, are laser etched so that you can feel that they are recessed, so those aren't ever going to fade with wear, although this won't be seeing much handling or wear once it's under a cooler. So we've been critical about the installation, but the other side of that coin is if they included a torque driver, it would become a very expensive product, and if they didn't do the witness marks here or give advisement on how to properly torque this product, then it would become inaccessible to a lot of users. So that wraps up the hands-on segment here. The installation is definitely something to be wary of and certainly careful of when you're doing it, but if you take your time, I don't think it's that difficult, and I think if you're careful, you should come out all right. And now we're going to go back to Steve.
Whether or not this thing is worth it, first of all, the contact frame does work. We noticed when we were looking around, there are some cheaper alternatives out there. The Thermal Grizzly one, it's about $35 so US right now. There is a group of cheaper, don't know which one came first, but cheaper alternatives that are in the $15 to $18 range. Now, the only concern we have with those, and we haven't tested them, we probably won't, is that the tolerances might not be as tight, and so you either sacrifice some of the gain or you might introduce some issues if you are actually overclocking, or you cut some of that frequency off the memory because it's running a little bit tighter than you think it actually is based on how it all secures to the motherboard. So it does work. We saw about a 7 to 8-ish degree reduction just with the frame, not with anything else. So they also, Thermal Grizzly has this lapping tool that you can secure the CPU into to get a cleaner lap if you're going to sand down the IHS. And that's what would help with the core-to-core deltas, where this frame, it did not benefit core-to-core deltas. We thought it might, but ultimately that problem, it's more in the thickness of the IHS and the variability in the thickness across the IHS, where, and we've shown this in the past, like with our video with Kingpin, where the surface sands down faster in some areas than others. And that's because the material is thicker there or thinner there, depending on the concavity or if it's a convex CPU IHS. So the thing you would have to do to fix core-to-core delta concerns would be lapping. And that's really only valuable if you're overclocking to a point where your single hottest core is limiting your maximum all-core frequency because you have no more thermal headroom to keep pushing the voltage and the frequency up. So if you're at 95 degrees already on your single hottest and your next two are, say, 75 or, well, 75 degrees would be a 20-degree core-to-core delta, which is what we're seeing, then that cuts off a ton of potential just on one core. So that's the way to look at this. In terms of pressure, it absolutely redistributes the pressure in a much more even way. And in theory, it reduces some of the flex of the CPU as well because of that. Whether or not we would buy this, well, it's cool from an enthusiast standpoint. It's sort of like the Rocket Cool IHSs, those copper ones, where this is kind of like a fun, you're an enthusiast, you like messing with your computer, you want to do something on a Saturday to burn some time and have an excuse to play with the computer without having to buy something expensive like a video card or a CPU or something like that. This makes sense there. It also makes a lot of sense and way more sense, in fact, if you do extreme overclocking, anything with dry ice, liquid nitrogen, stuff like that, that'll get far better value overall than normal consumer use, where a couple degrees, yeah, that helps. You know what else helps? Spending $35 more on a higher end cooler and getting similar performance gains and maybe even a noise reduction at the same time. So whether or not, this isn't like worth it for most people, but for the right enthusiast audience, we think it does well, and we'd be curious to see if Intel or AMD do anything in future generations to plan for these larger CPUs with higher pin count as the ILMs get kind of shown for where their weaknesses are. So that's it for this one. Thanks for watching. As always, subscribe for more. You can go to store.gamersnexus.net to help us out directly, where you can get stuff like the mouse mats that I have on the table here, or you can go to patreon.com/gamersnexus to get behind the scenes bonus videos, and we'll see you all next time.